Dan has a project he worked on recently at a wastewater treatment plant for a vertical pump. And Dan's going to go through how he utilized MEscope ODS videos along with MEscope traditional ODS utilizing accelerometers. So we'll get to see kind of two sides of the MEscope software during this presentation. A couple housekeeping notes. We are recording this webinar, so we will be sending out a link to the recording at the tail end of this. So if there's anything you missed in the webinar, you could review the recording later. Additionally, if you have questions, go ahead and type those questions into the questions box there in the little go to webinar tab towards the bottom of your screen there. And we'll try and get as many questions as we can answered. If you have additional questions that we don't get answered, you can always email them to us at webinars@5tech.com. And we'll get those questions answered to you via email. With that, let me hand things over to Dan and we will get going.
Good afternoon, everybody. Welcome to the webinar. My name is Dan Ambray from Full Spectrum Diagnostics. My company does vibration analysis in the field. We utilize the MEscope software a lot, almost every day. We also do training. We do AS&T and ISO based training, all different levels, different courses to satisfy anybody. And in fact, I've worked the last 3 or 4 years with Vibrant Technology doing some of their software training for MEscope. I have been an MEscope user for about 24 years, so about as long as they've been in business as Vibrant Technology. And I've seen a lot of changes, and it's all going in the right direction. And this latest version of the ODS videos is really something that's moving and changing. So as I speak, I was updating, 5 minutes ago, updating this presentation because of things that are changing. It's a rapidly changing environment, and it's hectic but fun to work with. MEscope ODS videos. It's a high-speed video vibration analysis, so we all know that. The video clip is processed with the optical flow algorithm that I'll go into in a couple of minutes here. It enhances the subtle displacement and rescales the amplitudes for us. This allows the user to see what the human eye cannot perceive in a video animation, either because the event is too fast or the displacements are too small, or generally both. Okay, so we're using high-speed video to slow down the motion, and then we're using this optical flow algorithm to lock into the displacement of a grid. It could be up to every pixel, but that's a little bit of overkill. We have a way of doing it that helps processing speed, but we're going to see how all that works. The first thing is the optical flow ODS method takes advantage of color processing. So we're looking to enhance the pixel displacements in the camera, and having a color camera. Color camera allows us to process the color changes, and they're actually looking at the intensity of the color as well. So my little colorful graph here is a 24-bit per pixel look at what the color representation is. So we have, using color processing, we have about 16 million colors we can look at. If you're using only black and white or grayscale, you get 256. So there's a big difference in how you can process the individual pixels in the image. And the optical flow algorithm enhances that. What is this motion that we're pulling out? This is the XY time waveforms from each video frame. When we're actually processing this, it's a two-dimensional analysis. So X and Y is what we get in the direction of wherever the camera is pointing. So there is a little bit of limitation. We don't get that third dimension, but we can view that XY screen in great detail. So if you look at the top plot here, this is the XY frame rotated as it's being rotated into the X plane. So if I'm looking for vertical vibration of this pixel in the middle of the frame, I'm rotating that frame 90 degrees. And so now I'm looking at a line, and I can track that pixel as it moves using the optical intensity of that pixel, the color camera I can see that motion. Not only do I see that motion, every pixel in the screen, I see that motion. So there's a lot of processing involved. So that's my vertical frame pixel motion. The next one, the Y frame, I'm turning on two axes at the same time. I'm doing a 90-degree pivot about the vertical axis and a 90-degree pivot about the horizontal axis. And now I'm looking at the other direction of motion. So from the top, basically, of the frame. So now I see the X and the Y. These two pixel motions are typically out of phase, but this is telling me exactly how much. It's a time waveform. So in that time waveform is the entire frequency range. I have phase for everything. I can do what's called an operating deflection shape from the time waveforms. And that's the base units that we'd be starting with. Operating deflection shape, or ODS analysis, requires that you have a frame of reference. In our case, you have to have a reference that stays put. In the case of time waveforms, if they're all acquired simultaneously, then we don't need to have the special outside reference point. If we're doing a frequency domain ODS, we have to have one point that's the reference point. We know how it's moving, and we have to have a roving measurement that moves around the structure. So now you're taking two measurements. You're taking an amplitude from the roving measurement, and you're taking a phase difference from the difference between the roving and the reference. I'll get more into that in a couple minutes here, but didn't want to confuse you. But a lot of people see this graphic and they say, yeah, that's what, now I understand. That's where the time waveform's coming from. Okay. This is the intensity vector. So part of the optical flow algorithm is looking at a grid, and I have a pretty sparse grid up there for my pump. I can put color contours on it so I can see where the motion is. I can also light up the intensity vectors, and the vectors are showing us how much vibration and what direction of vibration it's in. They're basically the time waveform. And remember, this is an XY plane, so they're only moving in two planes that we can detect. This image to the right here is the vector image. I've zoomed in on it. I see all my grid points. When I lay a grid point down, I can actually do the optical flow for every pixel on the screen, but it would take, that's about 1.3 million pixels. It would take a very long time to process. The grid analogy, I'd have a better grid than this, but I'm just using this for effect, would give us a limited number of points and a much faster processing speed. Typically, there's on the order of 22,000 or so points on the screen when you process a video. And you'll get something like this for every one of those 22,000 points as you walk through each frame. And then just another side-by-side mapping of this. Okay. But it's a process that there's two things here that we should really mention. One is this algorithm or the ODS software, the MEscope software, allows us to put a color contour on our mapping. So now we can see an amplitude representation of the response in the machine. We can also, and we can scale that to whatever our alarm limits are. We can also see a vector look to this animation. And you might not want to have it on here all the time, but you can see how the software works and what directions and how the image flows, or the animation image flows. This is the case history. This is an effluent pump, number 529, and it's given the vendor lots of problems. It has a lot of vibration. I didn't think it was too much, but we found a couple of problems we didn't expect. They thought some of the cracking grout around the base was producing a base problem where there was more vibration as you go up the cantilever beam structure. There's something you're going to notice right off the bat. This is a clean still image with a flash, and it's a very nice picture. This is the ODS video picture. And one of the limitations is trying to get a very big structure like this in the ODS videos format. because it's very hard to light. I'm so far away. I'm about 30 feet away, 40 feet away, trying to get an image of something that's moving at such a tiny motion. It makes things a little bit difficult. But that's one of the limitations that we'll talk about. That's the way the world works. We can always process videos in a different way. Okay? And one of those ways is getting a little closer on different planes and looking for things that the problem might be a result of, not just overall view and what we expect. So a couple of points. The overall image in ODS video shows a fundamental bending mode of the vertical pump near 468 CPM. 468 was, I think 466 was the speed that we were operating at. So there was a motion in the structure at very close to running speed. The motion is in line with the pump discharge line. So the discharge line, I'll show you a picture in a moment, comes out the back of the pump here. And in most vertical pump applications, you're going to have a stiff axis and a softer axis. So the softer axis is perpendicular to the discharge line, and in line with the discharge line is the more stiff response. So we'll have natural frequencies, and it turns out that one of them is very close to 200 or 468. The other one's close to 234, the off-axis response. Close-up video shows the same motion with some torsional response. The twisting is suspected to be a result of binding in the discharge line. Now I'm going to show you the discharge line and what the traditional problem has been that is causing lots of problems in this pump. ODS video of the discharge line flange indicates a response consistent with misaligned discharge line. It's been a long-standing problem for the pump. Here are a couple of videos, and the first one is the perpendicular mode at 234 CPM. So it shows up in my spectrum. It's a very low amplitude because there isn't anything to drive it. So compared to the running speed, there's very little energy in this mode. So it's really not being driven, but we still pick up this motion. It sticks out of the noise floor just enough. This is the inline mode, so a little stiffer, a little higher frequency. And you see a couple of things. There's multiple modes in here, it appears, and we're locking onto a natural frequency, so it's trying to follow the mode shape of the natural frequency. But at the same time, any residual unbalance in the pump looks kind of orbital, like you're orbiting around some point at the end of the motor here. So you get a little bit of twisting in it. What I think is going on at this point is this mode is being caused by the binding in the discharge line. And we're putting a big force in there. And it's very likely that this is close to a torsional mode of the cantilevered beam structure. And we've stiffened it into the operating speed range. Okay. This is that discharge line. It's a very big line. It's what is it, 60-inch diameter, something like that? Or yeah, 60-inch diameter is correct. There's where it buckles up. So the two flanges mate right here. They've installed these guides to help it, and it's about 1/4 of an inch off, which is a lot. And so they just had a problem historically. They made the pump a little too short and the line a little too large, and they couldn't get it to line up. This is one of their resolutions. They drilled some holes through here, made them oversized, and put this threaded rod in to try to draw in both ends. And really, this is much stiffer structure than this side. So really what they're doing is distorting putting loads into the housing on the pump side instead of on the discharge flange side. And you can see the motion in these two. There's a couple different frequencies, but you really shouldn't be seeing motion, like this, radial motion. It should be very small. We checked the foundation. We did some close-up videos and found some things that weren't expected. Okay, a couple of the things that we heard before we went there is the grout was cracking. The base has problems. There's a little bit of water. And in fact, there was a little bit of water right here in this section of the pump sand. We have 2 videos here, and I showed these to Mark just a minute ago, and he commented it's a very dark picture, which is true. So the lighting isn't all that great in this area. I could have cleaned it up a little bit, but it makes my point for me about using the color contour part of the software. So we have a tool inside MEscope that we can do color contours of our surface image and see the motion. Okay, in this case, I can see all this motion and everything appears to be linear, that it's pushing back and forth instead of moving vertically. I was expecting to see some vertical motion between the mounts here, between the bolts. It all looks like it's moving in line in the color animation, the color contours. So my first thought was we have a grout problem. This looks more like we have a slightly loose base plate. We might have a little bit of grout damage underneath this base plate that's causing it to slide a little bit. And all that force from the misalignment in the discharge line is causing this problem. This, however, is very small. Took some normal accelerometer measurements, and it's about 0.02 inches per second. So 0.02 is not a big number. For a foundation, if it gets above 0.07, that's kind of my indication that there's a foundation motion that shouldn't be there. Okay, in this case, we're about a third of that. So we have a very small motion in the base plate itself. We can still pick it up in the video animation, but it is very small. This is one of the other corners. Same thing. So they're both moving in the same direction. From that last image I showed you, it was on the other side. So one was here, one was there. It's all sliding motion, and the deck is moving. You can feel it. So this might be just fractions of a mil of motion, but you can feel a little bit of that while you're standing there. Not much, not a whole lot to get concerned about. The color contour plot shows that same motion, and it gives you a little better idea of how it's moving. Okay. This is optical flow. This is the intensity vectors all over the structure. So the same motion from before, it's my same image. I left the color contour on and I lit up the vectors. And you can see how they're changing direction and they're stretching a little bit. So what happens in this type of video, there's a flow of motion from that time waveform at each pixel, and the direction is coming directly from whatever the camera orientation is. If I zoom in on that a little bit, you can see how all the vectors are turning direction and stretching at the same time. Okay. Another feature, it's not something that you'd probably want to leave on, but just like this, it's hard to look at something like this and see little minute details. It's a lot easier to see when you have the color contour where all the motion tends to be, and then it does help a little bit to see how the vectors are flowing. And you'll see right away if something across this grout line is moving in the opposite direction, that would indicate a broken grout line. This is just small motion in the substructure. Okay, so we did this ODS vibration video. We found vibration in the machine that wasn't all that big. We found modes that were combined, potentially a natural frequency or resonance phenomena. We found a source for that in that binding in that discharge line was changing the natural frequency, possibly pushing it into the operating speed range. And we looked at the foundation and it didn't seem like there was a big deal there. That didn't seem like the root cause. The ODS, or the traditional ODS vibration analysis, is taking a transducer and walking it around, and you can see all my spots that are lit up. This is about 150 locations on this pump, and it's a triaxial accelerometer, so there's 3 directions of motion in each measurement. I have a reference transducer that was sitting here, and it stays put. I do take all my 150 locations with the roving transducer all the way around the pump, and I get 2 measurements. I mentioned before, it's a triaxial, so I get a little more than that, but I'll get a amplitude difference between the roving location and the reference, and I'll also get a phase difference. And the phase difference is telling me how is position 1 moving with respect to the reference, how is position 2 moving with respect to the reference. And you do that for all the locations and you get a nice image. It's taking a frequency spectrum, and I get phase all the way across the spectrum. So this is, one of those cases where you have a machine that can't be shut down, and you want to see how it's moving while it's operating under its own forces. This is the first mode. So the most obvious vibration in here, in the linear spectrum on the top, shows me there's a 1 times RPM. It's about 0.4 inches per second of amplitude. And it has some minor harmonics coming out of it. And it has a couple of low frequency peaks here as well. This is just some integration noise on a couple of the channels. I put it in the log scale, and I see a few things. Obviously, the 1 times is still the largest thing, but I can see all the amplitudes of the harmonics showing up. They're still noise level stuff. They're not really big. I do see my subsynchronous peaks, and these are the rigid body modes of the structure. Show you a comparison in a minute, but the big deal is what I think's happening is that discharge line, if it was relieved, this peak would come down dramatically. I believe that you're putting enough load and stiffness into that pump that you're pushing one of these natural frequencies very close to the running speed. And that's what this looks like. It's a distorted peak. It's not clean like you'd expect a 1 times RPM to be. Just a unbalance effect, residual unbalance. So I think there's a natural frequency in here. That's one indication. You got a broad peak, that's another. And the motion itself is very linear. If I have just residual unbalance, this motion will be a whirl instead of a linear vector like that. Okay. So what can I say about this? 0.4 inches per second, your normal alarm levels for a machine or vertical pump are 0.3 inches per second plus 0.05 inches per second for every 6 feet above the grade. So this is a very tall pump. About 3 of me is about right. So 6 times 3 is 18. Yeah, it's about a 20-foot tall pump. So I would have 0.3 inches per second. At the head level, I would have a 0.35, 0.4 somewhere up here, and then 0.45 up there. So right now I'm at or exceeding 0.4 inches per second. I'm probably okay as far as there's no real structural concern. Like I mentioned before, if I move that natural frequency away from running speed a little bit, either stiffen it or add mass, I can reduce my 1 times RPM response. This is that same image from another direction. And one other thing I wanted to mention, I'm still animating at 1 times RPM. My base, this darker green line is 0.057. So that is about where I'd start saying, hey, there's something wrong with the base, but it's above that level. So this lighter shade of green is below 0.057. So none of that is getting down to the actual bolted interfaces down here. So it's telling me there's the motion down here isn't causing all the vibration above. Okay. The other thing I see is over here on the discharge flange, there's color across the flange, so one side's moving more than the other, and that's a symptom of a misaligned flange system. Okay. Amplified mode shape response at force 46 is likely due to a pump natural frequency. The mode is very linear as opposed to orbital unbalanced response, as I mentioned before. These are the 3 peaks that I'm interested in. The first is my 1 times RPM, which we just saw, and I'm just trying to see the difference between them. This is at 270. So this is another mode. It's something strange going about it. It is in the discharge line direction, but there's some distortion in the piping. So there might be some torsional motion in there, something that's a little out. Pretty low level, not a real great mode shape. This is 175. This is the off-axis mode. Okay. So I had a little problem in the ODS optical flow analysis. It didn't have enough resolution between these two peaks, and it was looking at both at the same time. So I think I was having a little off-axis and little on-axis animation at the same time. This is the same plot, but I'm looking at it from above. So my 1 times RPM is directly in line with the discharge line. The 270 CPM response looks like a little rocking of the motor on the pipe stand, possibly a little bit of electrical box motion that might be a little off, and the off-axis motion. So not the discharge line, but perpendicular to it. Okay. These two levels, on a log scale, they look bad. On a linear scale, they're in the floor noise, as well as all these other peaks. So really the only one of concern is that 1 times RPM peak, and what do we do about it? They have to get rid of the original base. It's an 84 by 84 inch square that's grouted in with a hole cut in the middle of it, obviously. It is not that it's not supporting the pump correctly, it's at the wrong amplitude or wrong height. You have to add a little bit more height on the base plate there to get the two flanges to line up. Proposed plate is going to be a different plate grouted in, and actually this is it doesn't look exactly like this. This is my rendition of it. So I made it a little wider to give it a little more wheelbase. There's a cutout for some electrical lines that are right here on the pump structure, and it should allow us to resize the plate, get it to the proper location, and take the binding out of the discharge line. This is, as I mentioned, I'm going to go back a minute. This is the traditional ODS vibration analysis. And I mentioned it's with transducers, okay? I've already done the optical flow. I'm going to do this next. If I have I need to get real good details and an animation that is really nice. So we get these animations that we just walked through. In the MEscope software, I can take pieces out. So I can amplify this however I want. I can turn up the volume, and that's what I did in this analysis. So I wanted to see where that was, where this distortion starts to occur in the base. And it is distorting, but it's such a small level that it can't be distinguished. So even after turning up the volume, so my color contours went from a maximum of 0.4 inches per second down to 0.05. Any vibration in the base up to 0.05 is probably acceptable. And we're not getting that down into the base. We're getting something like 0.02. So 0.02 inches per second is about half of an alarm level. Okay. The animation is highly amplified to see distortions in the pump stand flange. That's what I was after. I wanted to see that distortion. That's what this is. So I've taken the entire pump off. I left this plate, and obviously there's a big hole in the plate for the pump discharge line, but I wanted to see how it deflects. So it's being caused by that motion in the discharge line direction. It's that loading that's being pushed back and forth, that natural frequency, and it is distorting the base, but not at a level that is a big concern. And here's the two traditional ODS analysis. If you are interested in the optical flow, the ODS videos, you also get the traditional ODS software package. So you can do more things with it. You can do this video overview of any system, and if you need real good details, you can go back in with a transducer and take really good, highly averaged data at any frequency range you want and see how the machine's moving. All right, this is it's a work in progress. I just made this up this afternoon. I had a couple of customers that wanted to know a point-by-point feature difference between the Vibrant software and the other vendor softwares out there. And based on what I know, and I don't know how the vendors competing with Vibrant software, I don't know everything about their software. These are the insights I know that they don't have. Everybody does, you know, a black and white camera. They have a light kit, things like that. Vibrant uses a color camera, but they can also use a black and white if they have to. You don't need to buy your camera from Vibrant. If you have another camera that's high-speed video quality, you can use that. So there's different features for different needs. The software features, MEscope ODS videos with the optical flow algorithm, only Vibrant has that. The other vendors do not. MEscope traditional ODS capability, this is really key because now we can do the optical ODS videos analysis and we can do traditional ODS in the same software package. Inside the ODS videos, there's image filtering. So there's flicker suppression in the lighting. This is one of the hard lessons. I went to Home Depot to buy LED lighting for this, and I bought the cheap ones off the shelf, and it turned out that when I took my first series of measurements on some machinery, it looked like there was a strobe light going off in the background because they were flickering. So you do need good lights, and that's part of the lighting kit that we would recommend. The other thing that the ODS software does is it flicker suppression. So it'll pull out that 120 hertz flicker that or 60 hertz flicker in some cases that's occurring in the lighting itself. It's not real vibration motion. There's background suppression. So the MEscope software has a low amplitude background noise suppression, and it has high amplitude background noise suppression. And it's user enabled. So you can manually do it. If you don't like how it turned out, you can refilter. So that's another thing that I asked to be added when we started working on the software wizard was I need a way to not completely get out of the software. I need to refilter this, and it'll take you back to the point that allows you to do that. You can rotate the image. So like my direction here with the ODS video, I had to turn the camera on its side to get the entire vertical pump in the field of view. When it came into the software wizard, it was laying horizontal. So that's another thing. You can turn the video any direction you want. So the rotation command works. There's different ways to show the shaft rotation. MEscope shows that by modulating in the time waveform domain. The other vendors, I'm not sure how they do it. I know they do some sort of shaft rotation. And we can also do shaft rotation for fan blades and for gearboxes where you can isolate the gear teeth. Signal processing, we do time waveform domain animation. We also do frequency domain animation. And some of the other vendors, they just concern themselves with the time waveform. Frequency domain animation allows you to see lots of other things, and that's what actually why ODS software in the first place was invented, for that frequency domain animation. We have signal processing that includes the FFT and inverse FFT, so you can manually do some of these signal processing ventures yourself and understand how they're affecting your machine to get the best possible image. There's high pass, low pass, and band pass filtering. There's integration and differentiation, since we are taking our video in a displacement application, we can differentiate it and turn it into velocity, and do it again and turn it into acceleration if we require. We do interpolation processing. As far as I know, we're the only ones that do that. And we do FFT averaging. Presentation-wise, we have a color contour plot that you've already seen. We have the intensity vector plot, and we also have side-by-side comparisons. We can look at two different modes or two different views simultaneously and see how the animation is moving. Options, we use any high-speed video camera. We have data acquisition front-end software. If you want to do your own traditional ODS, we have a kit that has all the hardware in it, and you use MEscope as your data acquisition front end, and everything's done in the same software. And of course, we have ODS video software training, and we combine that with MEscope software training. So if you want to build a pretty model like this, I show you how to do that in about a day. What does it cost? It depends on what you have. If you have MEscope software, it's cheaper. There are things that you won't need. But if we're starting from scratch, full package includes a camera, flicker-free lighting kit, tripods, the whole bit. It includes the VT420 Visual ODS Pro software that you're going to need for the signal processing, and it also includes VES 9000, which is the ODS video option. So from scratch, it's just under $20,000. Now that sounds like a big chunk of money. Our competition comes in at $30,000 to $35,000 starting out. If you already own VT620, which is the basic ODS software, you don't have to pay for the VT420 anymore. You just have to pay a signal processing upgrade. So $3,000, MEscope VES 9000, ODS video software, another $6,000. We're down about $4,000. Okay, so $15,400. If you already own VT420, which is the Visual ODS Pro software or better, you don't have to pay for any of that. You get a camera, you get the VES 9000, and now you're down to $12,400. If you own everything, or you have your 420 software or better, and you have your camera, you don't have to buy a camera. All you need is that ODS videos package. So you're down to $6,000. So if you're a user already, there's a discount. I think Mark offered a discount last week's video. Is that still in play, Mark? That 10%?
Absolutely. Yep.
Okay.
Yep.
So
if you get a 10% off if you reference ODS Videos 10 when you talk to your reseller, or if you are going straight through Vibrant for your sales, for your MEscope sales. So
there you go. So
yeah.
Users get a big discount just from already using the software, plus a 10% drop off of that. So that's how pricing lays out. Training, this is handled on a per vendor application. Usually it's best if the trainer, which is me, goes into your site. So if I'm going to teach you something and you want to have examples from your plant, and we'll just go out in your plant and do some videos off of your machines. That's a big part of the learning process. The other part, it's usually a 2-day training. One of it's doing the videos and processing them. The other is building some models in MEscope so that you can do traditional ODS if you want to do that. It's kind of up to you. If you want to do 2 days on site just to do videos, that's fine with me. If you're never going to do the traditional ODS, then we don't really have to worry about that. So it's whatever you want. It's $5,000 for up to 2 students on site. If you have extra days you want that are going to take some more time, it's $2,500 a day. If you have an extra student, $1,000 a piece. So it works out pretty good. It covers all the expenses. It covers the training, everything. Okay. So we have a workbook. We have a 14-day license. If you want to take the training before you buy something, you can also do that. What's included in the MEscope ODS videos kit? You get VT420 ODS Pro software, so you can do traditional ODS analysis. You get VT450, the optical flow ODS option. You get VT800, which is the high-speed camera kit, and that kit includes one of our choices that the Vibrant people have been using is the Chronos 1.4. It's a high-speed color camera, and it's manufactured in Canada, but it's a very good camera at a very good price. It has 1280 by 1024 resolution, so pixels, 1.3 million pixels in any image, and it's taking about 1069 frames per second. You can speed it up, slow it down. You can use less resolution to get more frames, and there's little games you can play, but typically the 1280 by 1024 and the 1000 frames per second is a pretty good rate to get the best results. And you get lighting, you get the flicker-free lighting, LEDs, stands, all that. And I've come to the end of my rope. Do we have any? Do we have any?
We do have one question. Yeah, it came up. It says, how is anti-aliasing handled in video processing?
Anti-aliasing. Well, I guess it would be with processing speed with the 1069 frames per second.
Correct.
It gives you about 530 hertz of frequency range. So that's your cutoff. If you want to go faster, 1069 frames, you divide it by 2, and that's 530. Right. So that's basically how the anti-aliasing works. You still have that Nyquist frequency. Some use 2, some use 2.56. Vibrant uses 2, and that'll eliminate your aliasing. You can do higher frames per second. The camera will actually do about 42,000 frames per second, but your resolution is degraded quite a bit from that. So you can look at, high-speed images of, somebody shoots a bullet through an apple, and you can, trigger on that and see all kinds of really high-speed photography type stuff, but there's really no reason to have that many frames for a ODS model. Good enough?
That'll do. Another question came in. How long does it take to make videos? I know we talked a little bit about that last week, so we can go ahead and
I thought about this right before the class. I've been doing a lot of videos, and it doesn't take long to take the data in the field. It's more setting up the lights, making sure everything's right, everything's steady, and you take 1 second worth of data and you're done. And you go do another view. So I usually, on any machine of interest, I might take a dozen videos or so and look at the foundations, look at the motor feet, look at any interface, take an overall shot from multiple directions, and make sure I've mapped it pretty good. When you pull it into your computer and you start through the wizard, there's like a 5-step interactive wizard that you can use, and you process it how you like. It might take up to 7 minutes, 7 to 10 minutes maybe, to process an image, and then looking at it and putting color on and vectors and all that. Some of the signal processing might take another 15 minutes. So I'd bank on very little time in the field, probably a couple hours to get a single machine the way everything wants and all the lighting and everything. When you bring in those dozen or so images, maybe 15 minutes to pull the image in and another 15 minutes to analyze it. So a half hour an image, another 6 hours maybe to get a good story going and build some conclusions.
I think it also varies too how the density of the points you're choosing.
Yeah, that's
how much you're going to be processing.
10 minutes is about right. If you go pretty sparse resolution, your movies are only as good as your resolution. So on the high end, it might be 15 minutes. On the low end, it might be 6-7 minutes. So it averages out, 10 to 12 minutes, I guess, for good resolution.
Great. Let's see, another question just popped up. How small of motion can you measure? I think he's maybe referring to frequency.
Well, amplitude, I think.
Or amplitude,
When you go back to this base, this was the, now I go back even further. I don't think I had that, like this motion of each one of these pixels moving. I can't remember what the displacement is, but it's very small. It's on 1/10 of a mil, something like that. It's pretty low. I can, if you have that guy's email address, I can find out and email him a number.
Yeah, we'll get that to you, Paul.
Yeah, right now I don't know.
Okay.
But I mean, this was, oh, well, I have an idea, I could convert this. Well, this plate, the motion, it goes yellow and it gets about to the edge of the yellow, which is 0.021 inches per second. So at 446, I could calculate it and it would be super tiny. But I'll do that for you and send you an email. And maybe the next webinar, I'll go over questions first and then
sure.
Questions from the last time.
Okay, good.
All right.
That's it for questions right now. If you have additional questions, feel free to email those questions to us again at webinar@vibetech.com, and we'll get those questions answered for you. And you should also get a link in your email here soon, probably towards the end of the day, after this recording is processed, and you can go back and view the recording of this webinar. With that, we'll go ahead and finish it up, and stay tuned. We're probably going to do another one next week, right, Dan? I assume.
Once you start, you really can't stop.
There you go. So stay tuned for that. We'll send out another announcement for the next webinar we do here, and hope everybody has a great afternoon, and we'll talk to you again soon. Take care.